Welcome back. In this video, we're going to be talking about CAM, specifically CAM using Fusion 360. And what CAM is, it stands for Computer Aided Manufacturing. And as it sounds, you're using computer programs, Fusion, to manufacture the parts that you have designed, in our case, in SolidWorks. So the first thing that we're going to have to do is transfer our part that we just made in SolidWorks into the new software, Fusion 360. And so to do that, we're going to go over here and click upload, and we're going to be uploading a file. So we're going to select the file we want to upload. I have it stored under test and test part 1. This is the part we're going to be manufacturing, so click on that, put it in here, hit upload, and you'll see it uploads on the left here. And it does take a little bit longer for some reason in Fusion to upload files. I'm not exactly sure why, so just be patient with it and let it upload. Once it's uploaded, you can hit close and go ahead and open this part by right-clicking and hitting open. And now we have our part that we made in SolidWorks into Fusion, as you can see here. So the first thing that we notice is they give you a flat plane as kind of a reference plane, and we want this part to be sitting flat on that plane. That way when we're going to machine it, it kind of looks better, it makes more sense, and we have our X and Y planes of the part in line with the X and Y planes of this larger plane here. So to rotate this part to make it flat, so to rotate this part, what we're going to be doing, first we're going to go over here. This is kind of similar to the idea tree in SolidWorks. It tells you where the origin is, X, Y, and Z. It tells you the name of all the top views, some of the document settings, all that kind of stuff. And also in here we have all of our parts that are currently in our Fusion file. So we only have one part in right now. It's body 1 is what it's labeled as. It's the part that you see here. So we're going to go ahead and click on this, right click, and then the first option is move/copy. We're going to be moving it. Let's go ahead, hit move. What we're going to do is, this is kind of like how you rotate things. With this knob adjustment here, you can translate it, you can rotate it, do all that kind of stuff. Just want to rotate it 90 degrees so that it is flat with our plane. So rotate it till it reads out 90 degrees, then hit OK. And now our part is flat in line with our plane. So now that we have it in line, next thing we're going to do, you can play around. So right now there's like, 6 tabs that you can choose from in Fusion. So design, render, animation, simulation, manufacture, and drawing. We're doing manufacturing, so we'll be choosing this shortly. But if you want to play around with design, you can. So say you bring it into Fusion and maybe you like the way Fusion works better, you like using the Fusion features and that kind of things. You can, if you want to, now go ahead and extrude something else, do cut extrude similar to what SolidWorks uses. You can draw lines on a sketch, all that kind of things. I'm not very familiar with the features, because I don't prefer using Fusion for doing CAD. But if you want to, you guys can play around with it in this design tab, do whatever you need to. So we're going to head into this manufacturing drop down, and you'll see our toolbar on the top changes as you change from design to manufacturing. So all these kind of options on the top here. First options you have, obviously you have the 2D options are labeled here, as well as the 3D options, and what these are, is it's kind of the type of toolpath that you're going to be machining this part with, right? And so there's all sorts of ways you can cut it apart without a CNC router. You can drill something, you can cut it on a bandsaw, you can mill it, all that kind of thing. And a CNC router can do a lot of those things just by itself, and that's why it has all these different options. So you can see there's drilling options. The 2D options include things like facing, which is similar to like a mill cut that we've been doing in the past. 2D contour kind of goes around the outside of a part. 2D adaptive clearing is what we're going to be using, you'll see, to do kind of some like the inner workings of this. There's also more complicated things like 3D adaptive clearing. There's some parallel face stuff, some curvature things. We don't really mess around with that kind of stuff. But there are a lot of options, and that's why for this video I'm going to be making it relatively simple. I'm just going to be doing I believe three of these 8 options, because those are the 3 that you mainly used for robotics because you're not creating insanely complicated parts. They're mostly two-dimensional, sheet metal, basic drilling, pocket clearing, kind of simple things like that. And so, first thing we're gonna do whenever you start trying to manufacture a part is you have to make sure that your units, just like in SolidWorks, make sure that your units are correct. So right now the default is millimeter. So we're gonna go ahead and click this and make it inches because all of our drill bit sizes are in inches. So we want to make sure we have kind of consistent units all the way through. And then the next thing we're going to do is we have to set up our stock. And what that means is right now we have a part, but in order to manufacture this part, it has to come from some sort of stock material, right? That's kind of how it works. And so for this part, it's 1/8 inch rolled aluminum sheet metal. And so we need to define our stock as what is 1/8 inch rolled aluminum sheet metal. So we're going to go over here. It's the first kind of tab button next to manufacture. It says setup. We're going to go ahead and click setup. And you can already see it somewhat predefines our stock material as this yellow box. However, it's not exactly correct to what we actually have. So we need to go ahead and edit the settings, make sure it is what we actually have on the CNC router table. So first thing I always do is it comes with kind of built-in offsets. So an offset is just like how much extra material we have. You can see over here how much extra material we have on the piece. And so I always make the side offset 0. And the top offset kind of depends on what material you have. So right now in SolidWorks, we made the height of this part to be 1/8 inch, which is exactly the thickness of our rolled aluminum stock. So we're not going to need any offset because that already is the height. But say, for example, you want to make this 1/8 inch tall part, but you only have, say, 1/4 inch thick aluminum plate, right? So your offset is going to be an extra 1/8 of an inch because an 1/8 of an inch of the part plus an extra 1/8 of an inch. As you can see, right here will create thickness. Oh, what the heck? Hold on. 125. You'll see we'll create the overall thickness of 0.25. So if you have 0.25 inch thick stock, you're going to want to have this height and will be 0.25. But our stock is 0.125, so we're going to make sure our offset is 0. And that's all set. The next thing we're going to do is define which direction our Y is going to be and which direction our X is going to be. So this one actually looks pretty good. So Z is up, obviously, Y is kind of out in this direction, and X is in this direction. You always want Z to be going up. And the X and Y kind of varies. So if you have, you want a specific orientation of a part, so you have like a really, really long part that only fits on the router table in one direction because it's like 5 feet long or something like that. You're going to want to make sure your part is oriented in a way that it can be cut out on the table. And so to change that, I'll change it just as an example here. You're going to go to model orientation. I usually select Z and X, so hit that. And the blue box, similar to SolidWorks, the blue box is what you're currently working on. So right now it's asking for me to select the Z axis. And so our Z axis is going to be staying the same, perpendicular to our part. And then if you want to go ahead, you can select X axis and you can change which direction it's going. So right now it's going kind of in this direction right now. If we want to change it, what we can do is we can select an edge that we want the X axis to lie upon. So right now it's kind of lying upon this edge right here. If I want the X axis to be swapped with the Y axis, for example, I could then select this edge, and now you can see the Y axis is in line with that edge. And then so right now the arrow points in the positive direction, and so this kind of depends where you want your home position to be. But if the corner of your material or your stock is, say, down here, you kind of want your X positive to be, along the length of the part, and your Y positive to be along this length of the part as well, or however your orientation might be. So I'm going to swap the direction that the X positive is going to be. So go ahead and hit swap X, and now you can see the X arrow flips directions, and so does the Y because they're kind of linked together. And that looks a little bit better to me. So the next thing I'm going to do is select where I want the origin to be, and you can see these kind of XYZ marker right here. The little white dot is the current origin of the part. Right now it's right in the middle of the part, and I'll explain why you want it this way, but you want the origin of your part to be in one of the corners. And I'll explain later in the video when I'm out at the router table showing you guys why that is. But for now, just trust me. So to change it, we're going to go ahead and hit stock box point. You can do model box point, doesn't really matter in this situation. Again, if you have a stock that is thicker than your part, so like a 1/4 inch stock but only an 1/8 inch thick part, you're going to want to choose stock box point. Again, I'll explain why later. But if they're the same thickness, it doesn't really matter. I've just kind of grown to use stock box point because it works in every single application. So hit stock box point, then click this little tab right here, which is stock point. You're going to be selecting which point of the stock you want the origin to be. I want it to be down here in this corner. You kind of want, like your X and your Y's to line up with the two edges of the stock material. And then go ahead. The last thing we're going to do is select which bodies we're going to be machining. So hit this, hit your body you want to be selecting. It'll turn blue when it's selected, and hit OK. So now we have set up our stock material with our origin in the corner, the correct offsets, which in this case is 0 for everything, as well as the correct X and Y orientation. So next thing we're going to do, I kind of want to talk about some basic principles of machining. And what I mean by that is the main thing to know is you always want to do drill holes first in the majority of cases. And then you always want to do like the final cutout last. You don't want to cut out the part, like cut out the whole edge of the part and then try to go in and do the other stuff, because the part won't be free from the table, right? Because the way it works is you've got, kind of like the model shows right here, you got a huge sheet of aluminum. If you cut out the border of the part, this whole part is going to be separate from the rest of the stock, which is secured to the table, and the part's just going to come up, right? Because if this is like the stock material, this whole gray box right here, I might only be drilling in 4 bolts or 4 screws in these 4 corners, and not in the actual part. So if you machine the edge of the part, it's just going to come free, and that's not good. So always machine the edge of the part last. I like to machine drill holes first, and then what you need to keep in mind is if you have like multiple parts, if you have like a part here, a part here, a part here, parts all around, like kind of in tight spaces, what's going to happen is they're going to start vibrating a lot, because as you start taking away material, less material means obviously less strength. So if you have like a lot of small parts or a lot of parts that have big cutouts that are next to each other, if you're trying to machine like huge pockets of material out, really kind of aggressive cuts, it's going to vibrate, it's going to do really bad things. So that's why you need to either do 2 things. Either you need to space out your parts like further than like right next to each other, or you need to be cutting out one part at a time. So maybe you cut out this piece right here, and then if you want to cut out a piece right next to it, you need to kind of change your 4 screw locations to be closer to the part, cut out that part, move along, kind of go systematically slower, and more methodical. With that being said, if you're not doing really aggressive cuts, and you're not bolting or you're not screwing down the part like wicked from, so if this is like a huge sheet of metal, say 3 feet by 3 feet, and you're only cutting out a small part, you don't want to screw it down at the very corners. You'd want to screw it down kind of somewhat close to the part. That way there's just less room for vibrations and things like that. That's just a couple things you need to note. I'll give you more tips as we go along this tutorial, because there are a lot of things you need to kind of keep in mind, a lot of things I made mistakes on, a lot of things that I learned that I'm trying to teach whoever's watching this video about. So with that being said, a couple other things. Machining is actually a lot more difficult than you think it is. So you may create a tool path in Fusion that looks great. You do the simulation, which I'll tell you guys how to do later, and everything looks great. And you go down and cut the piece on the router, and it vibrates horribly, and the cut is really ugly and not what you want. And so just keep in mind that the cuts that you make or the cuts that you draw up in this manufacturing software aren't necessarily going to be how the part's going to come out in the final, and it's going to be a bit of a learning curve to it. So first thing we want to do, like I said, drill holes first. So usually the order I do is I do drill holes first, then I do kind of like bigger pockets, and then the final cutout. So to start, drill holes are the easiest thing to cam up or kind of like create tool paths to manufacture. What we're going to do, go ahead, hit the drill tab up top. A little box over here is going to pop up, and that's at these box on the right always asks you a bunch of things. It asks you for like plunge feed, like feed rates of the bit, RPM of the bit, what you want to cut, a bunch of stuff. And what they ask for is different based on which tab or which tool path you're going to be using. So for a drill bit, a couple things you need to know. First thing we need to do, as always, in every single one of these different types of cutting paths, is select what tool we're going to be using, because Fusion needs to know the diameter of the tool, mostly the diameter of the tool, right? Because it has to know the diameter of the tool so that it can know where it's going to go, how far away it's going to be cutting from the stock, just a bunch of things it needs to calculate. Anyways, so we need to put a tool into our software. So what we're going to do, hit select like I did, hit this little plus button right here. And I always use the flat end mill. It doesn't really matter unless you're doing something like crazy, like a dovetail or something, which we're not going to be doing. So just choose flat end mill, and then you need to put the diameter of the bit right here where it says diameter. So this hole in SolidWorks I know was 0.25, I believe. So just hit 0.25 and hit OK. Hit OK again. And now you can see right under this tool category it says number 1 tool, which is our quarter-inch diameter flat end mill bit. So next thing we're going to do is we're going to select RPM. And so all these boxes under feeds and speeds, I have put all the feeds and speeds for different materials, different bit sizes, different everything in a Google Doc that you guys can print out. Keep it probably one by your computer and then also one by the router, just so you have kind of two places of reference. And what it looks like, I'll put it onto the screen here. This is what it is. So it gives you for like all the different mold aluminum, tube aluminum, drill holes, smoothing passes, polycarb, different types of wood, plastics, all that kind of stuff. I have all the RPMs you need, all the feed rate you're running, the plunge feed rate, a bunch of different stuff I'm going to be talking about very shortly. So I'll just keep this kind of right here for now. Oh, whoopsies. Hold on. Keep it right there for now. Okay, so we can see that we need for drilling holes with the drill bit. Right here we're using the 0.25 single flute bit. It's the most common bit that we use when we're doing machining. We can see we need a 5 inch per minute plunge rate, a RPM of 15,000 RPM, as well as the rapid out command. And I'll show you guys where to access all those. So first thing we're going to do, 15,000 RPM, we already have that set in. Plunge rate, you need to make this 5. So go ahead and plug that in. And then the retract rate and the feed revolution don't really matter for drilling. They will matter for other things, but for drilling holes, it doesn't really matter. And you can also see on the other document, so this is, we're drilling with a single flute bit. So these are the settings that I recommend you guys use. But you'll see, good thing to note, I'll point out right now, if you're drilling a hole with a drill bit, a lot of hand drills run at roughly 3,000 RPMs, and then like drill presses can run slower than that. But for machining with a CNC router, because drill bits are only made to run on like a hand drill normally, they like to run at slower RPMs. That's how they're designed and built to be made, to be used. So I run drill bits, not the single flute router bit. I run drill bits at 4,000 RPM with the same 5 inch per minute plunge cut, and the same rapid out command as well. Just so you guys know that. So we have all of our settings in here. The next tab is always the selection tab, and that means selecting what holes you want to drill, what pockets you want to machine, what you're trying to cut out essentially. So for this, you can see it's asking which hole faces we want to select. We're going to go ahead and just select this face right here. And you know it's selected, one, because it's blue, but also because these kind of toolpath lines show up, and the toolpath lines show you what the tool is going to be doing. So you can see the red line, the red dot right here. It's going to be going in, down, cutting out the material, and coming back up again. A very simple toolpath. The next important thing to know is you need to tell the router where you want to start the cut, where you want to end the cut, how deep you want the drill hole to be, all that kind of thing. And so the two kind of settings that you're going to want to be playing with is top height and bottom height. So we want the top height to be the model top. That's what we kind of want the drill bit to start cutting from, the top of the stock material. And then the bottom height, we're going to want to be the model bottom. Now, this is a good thing to note. So, like I said before, the way you do it in CAD, or in CAM rather, is not going to be how the part necessarily comes out. And so there are some things you can't really deal with, but for drilling holes and kind of making it as accurate as possible, the one thing that I do is I always run the drill bit 1/100th of an inch below the bottom of the material. And so the reason for that is you want, like I said before, we define the origin of the part to be right on the top of that surface, right on the 0.125 thickness. You can see it right here. It's right on the very, very corner. However, say for example you home, just like I had to do later, you home the machine 0.002 of an inch above that, which isn't very much. I've done it before. If we're only, say we're not putting this offset of 1/100th of an inch down, it's only going to go down the 0.125 inches of the stock material. And because of that, you might be left with that kind of 0.002 of an inch that you messed up when you're homing it. It's going to be now on the bottom of the part, and you're not going to be drilled through the entirety of the part. So yes, we are going to be, if you do it correctly, we're going to be putting a little 1/100th of an inch indentation on the router table, and you'll see that the router table has so many marks on it from me doing this, but that way you ensure that you really get the drill holes to go all the way through the part. So now that we have that set, what I was talking about before with the rapid out command, with the drilling, there are a bunch of ways you can drill. Is rapid out, which is kind of the one that I'm going to be recommending for you guys, but there's also, you can see there's like 10, 15, 20 other things you can be doing. There's even a custom one you can do. And it all gets a little bit complicated. There's tapping you can do in here. There's chip breaking, which is important. You're doing harder things like steel. But for aluminum, we're just going to be selecting the rapid out command. And that's it for drill bits. It's relatively simple compared to some of the other stuff we're going to be doing. And so now that that's selected, we can see, you can see the transparent chuck of the drill. You can kind of see the bit going down and out, and it gives you an overview of what the toolpath is going to look like. This one is very simple. It's only going to go down and back up again, and that's it. So next thing we're going to be doing after the drill bit is going to be machining out these 3 pockets right here. And to machine out large pockets, or to machine out relatively small pockets, I always use this 3D adaptive clearing toolpath. If you have huge pockets that are like, I would say more than 2 inches by 2 inches, I would recommend the 2D toolpath, which we'll go into how we use that one later in the video. But for relatively small pockets, we're going to be doing this 3D adaptive clearing toolpath. So go ahead, hit on this, click this. We're still going to be using the same 1/4 inch bit. You can already see it kind of pre-selects the 1/4 inch flat bit. And this is where some of the more complicated feeds and speeds settings come in. And feeds and speeds has been, there's so much stuff on the internet about what the ideal feeds and speeds for cutting aluminum, wood, all the materials are. You can go ahead and Google it, look at kind of reputable sources, if there are some. But I'll give you guys kind of what I use, what this router can handle, and kind of what's the best way to have a somewhat safe cut that's not too aggressive but not too slow either. And so you can see for rolled sheet aluminum, 15,000 RPM, 35 inches per minute for the cut feed rate, the same 5 inch per minute plunge rate. However, there are 2 new settings right here. The ideal feed per tooth is kind of the most important one. It's what all the feeds and speeds are based off of, as well as the depth of cut, which is kind of more self-explanatory. But I'm going to talk a little bit right now about what the ideal feed per tooth is and what it means and how important it is. So, ideal feed, so we have a single flute bit, right? And every time, because only one flute, that means every revolution of the bit is going to take out essentially one chunk of material of aluminum. And so if you can kind of think about it, the faster that the bit is going, it's going to be doing more RPMs and essentially taking out less material per cut if you have the same speed of the bit, right? And so what this number is, the 0.0222, it's essentially a representation of how big that chip that you're cutting is going to be. And so you can change how big that chip is going to be. If you want a bigger chip, you're going to run either slower RPMs or a faster feed rate, and then the vice versa for a smaller chip. And so we kind of, why this is so important is because how big the chip is really tells you how well you're machining the part, how much more the machine can handle, or how, if the machine's too stressed, if the chips are too big. It can tell you how smooth your cut is going to be, how fast it's going to be, how accurate it's going to be, just so many things. And so a lot of times when you're looking up kind of ideal feeds and speeds, you're going to get a number for the ideal feed per tooth, and you want this number right here, or whatever number they give you, to match what you're going to get in, I believe it is the feed per tooth category right here, which I'll confirm in a minute. So we're going to go ahead and put these settings in, all these settings that I have right here. So I've kind of memorized them. 15,000, 35 inches per minute. You're going to want to go ahead and put these into all the categories I'm putting them in right now. So lead in 35, lead out 35. Ramp feed rate is 5. Oh, what am I doing? 5. And plunge is also 5. Okay, so one thing I've got to mention, which is actually really important, is that you need to make sure when you're defining your... Oh, that is weird. I don't know why this is here. Remove, delete tool. I don't know why that's there. One thing you need to do is when you define each other, you need to make sure that you have it as a single flute, because it kind of depends. So if like I told you before, every revolution, if you only have one flute, is only going to cut one chunk of material. But if you have more flutes, you're going to cut like 3 pieces of material per cut. So it really depends on how many flutes you have. So we're using a single flute bit. So make sure you put that in there. Hit yes, hit OK. And now we're going to go back in again and make sure that all of our settings are correct. Just make all these 35, 35, 35, 5, and 5. And now we can see the feed per tooth is 0.0023, which if we reference back to our document, that should be what it is. Yes, 0.002333. So this is kind of, like I said, how big the chip is going to be. And you can do things to alter it. So say the machine is cutting too aggressively, or it's like vibrating too much. You think it's creating, the chips are too big and it's too aggressive. What you want to do is aim to get this number right here down. Some of the things you can do is you can increase the RPM. You can see that'll decrease the number a little bit. You can also decrease the feed rate down to like 25. You'll see will also bring the number down. So there are things you can do to bring that number down, to have a little bit more of a less aggressive cut, is how I would describe it. So now that we have all these numbers dialed in, I recommend you put all these numbers that you see in front of me into these boxes. We're going to go ahead and hit the next tab, which again is the selection tab. And I've played with this a lot. I've had a lot of issues when I first started learning how exactly to get this to work, because I had so many errors pop up and couldn't generate tool paths and just a load of issues. And so what I'm going to show you guys is how I do it. I think there are other ways to do it that might be better or maybe not better, but it's kind of how I tend to do it. So I turn off rest machining and stock contours. For geometry, I select selection, and I select tool inside boundary, which kind of is what it sounds like. You're going to be machining with the tool inside of the boundary that we're going to select. So tool inside boundary. And it's going to ask you machine boundaries that you want to machine. I want to machine this pocket, and this pocket. And as this kind of tool inside boundary suggests, it's going to be putting the tool inside this boundary and machining inside of the boundary. So that's all set. The next one we're going to be going over to is the, again, the height selection tabs. And similar to what we did with the drill holes, we're also going to be wanting to select the top height to be model top, the bottom height, model bottom, and we'll also be putting in that 100ths of an inch kind of like cut below the bottom of the thing. And this one is really important because I made this mistake the first time I did it too, where I did not put this extra 100th of an inch. And what happens is, I think we did it when our first cut even at Trace's building, not even at my house. We didn't do this, and what happened was we had about a 2 to 3 thousandths of an inch layer of aluminum along all these pockets, and you can't really get rid of that. Like with the drill hole, you can kind of get the same size drill bit in there and go back in by hand and drill it out. With the huge pocket, if you have like a layer of aluminum still left over, there's not much you can do about it. So you really want to make sure you're giving yourself that extra bit of error and putting in that 100th of an inch below the bottom of the the model. So that's all set. Next thing we're going to do is jumping into a little bit more complicated settings. I always turn off, the first thing I do is always turn off this stock to leave feature. I don't want to leave, so essentially it is what it is, right? Would you want to leave a certain amount of stock radially, which will be like around the corners of it, as well as axially, which would be like along the flats of the pocket. I don't want to leave stock. I don't know why you would really want to, honestly. If you have like a less accurate machine, I guess you would want to do that. But turn that off. We have a bunch of settings here. So tolerance, I don't really mess around with. You can kind of see right here, like the higher tolerance that you have, the more smooth a curve is going to be. But they recommend 4 thousandths, which is kind of close to the accuracy of our machine anyway, and so that is what it is. I don't really change that setting. Minimum cutting radius. This is an important setting. It can give you some trouble if you're not careful with it, but it can also be really useful. So, what it is kind of is what it sounds, right? So a cutting radius of a machine is just like a radius of a circle. If it's trying to do an arc or something, it's how tight that arc's gonna, the minimal radius of that arc. And so if you have like a really, really tight minimum cutting radius, the machine can kind of get into smaller corners essentially, and it's going to be doing a lot quicker and finer adjustments. If you have a larger thing, it's going to be a lot more smooth, kind of fluid cutting, which usually takes longer, usually is quicker but less accurate. So it kind of depends on what. I usually don't change that setting unless I really have to. So say like I need the 0.125 inch radius on this corner right here, I'll make it 0. But right now, it's going to be yes, this picture actually is a good example. If you need to get into like a tight pocket, as you can see, pop up. Hello. If you need to get into a tight pocket, like on the left diagram here, if you have a larger minimum cutting radius, you're going to get an example of what the bottom or what the right picture is, which is you're not going to be able to get into the corners as easily. So I usually keep that where it is unless I really have to get into some tight corner or some tight pocket somewhere. And the next thing below it is this direction of cut. And this is pretty important, although at really higher RPMs it doesn't matter as much. Pretty much the bit is always turning clockwise. However, if you want to machine the border of this part, you can go two ways. You can go kind of like in a clockwise manner like this, or a counterclockwise manner like this. And because the bit is turning clockwise, if you go a certain direction, it's going to kind of cut into the material more and really dig itself in, versus the other direction is going to kind of skid along the surface. So a conventional cut is the more traditional way, as it suggests. The conventional cut is kind of going the correct way to get a better cut, not necessarily a smoother cut, but a cut that's going to do less damage, less wear on your bits, less wear on the machine, and it's kind of just the more correct way to machine the material. However, you use the climb cut when you want more detail and more smoothness. We're going to keep it for this adaptive clear, for all adaptive clearing for the most part. I keep it conventional, and then for the kind of like finishing or smoothing pass, I usually do climb, which we'll go over in just a minute. So keep that conventional. Next thing as an option is the maximum roughing step down is what they call it. Pretty much it's depth of cut, and you get that number from the worksheet. So for rolled aluminum sheet, depth of cut is 0.03 inches. So go ahead and put this in as 0.03 inches like that. Fine, step down is already automatically created. Don't worry about that. And the next, so in this kind of like, I don't know what they call this window, passes window, the only other real thing that I use is what they call smoothing. And I use this whenever they're doing, you can kind of see, I do it whenever we're doing really accurate things. So bearing holes, maybe you need a hole to be exactly 3/4 for some rod or something like that. And the reason for that is because the way the machine works, it's connecting a bunch of points. It's kind of like a connect the dots in an essence, if you don't have smoothing on. So it'll say like go from 0.00 to 0.11, which is going to be a straight line. And so if you want an arc, maybe it'll do like a bunch of points that kind of create an arc, but they're still only points and still only lines, so it's not a completely smooth surface. However, if you have smoothing turned on, it alters what they call the G-code. The G-code is kind of those commands. Like a G-code line would be 00201 or 11. It's lines of code that tell the machine where to go, kind of like coding autonomous, honestly. And so there are different types of G-code. There's basic G-code, like X and Y. So X1, Y1 would be like the basic kind of G0 G-code. However, there's more complicated things, for example, arcs, which is what we're using for the smoothing command. So an arc will actually, I believe it would be like I1, J1, so it's I's and J's versus X's and Y's. And that, instead of using like a bunch of dots that they're connecting, it actually creates a nice smooth arc if you choose this smoothing command. So for bearing holes, you want a nice smooth circle. For, a bolt that you're trying to put in, you want a nice smooth circle. So we're going to turn smoothing on, and the higher tolerance you have, the more smooth the arc is going to be. 4/10,000ths is plenty. That's high enough number. You can go down even if you want to like 1,000th, but just keep it at 0.04. It's a lot simpler when you're trying to do it over and over and over again. So turn smoothing on for important things like that. It will create kind of one extra finishing pass, so it takes a little bit longer, but it needs to be done if you're trying to do bearing holes or things like that. And then the final tab, there's only two main things really. First thing, turn off helix and make it plunge. Helix will kind of enter the material in a helix circular form, so it'll like go in a circle and plunge down lower and lower and lower. It takes a lot longer to cut with a helix cut. That's why I never use it. I just use the plunge cut. It's definitely more aggressive, but it's so much faster. So make that plunge. Also lead-ins and lead-outs. You can play with it. You really don't need lead-ins and lead-outs transitions. They're not that important. So I just make them 0. It does save time. It's a little bit simpler, unless you need to worry about things like that. So that's all the settings that generally need to be used for cutting out pockets. Now there are some other things too. For example, this is also an important feature: order by depth. This is order by area. If you're doing multiple pockets, so like 3 pockets, I want to order by area, because what that means is it's going to cut out all of this one pocket, then it's going to cut out all of this pocket versus all, and then cut out all of this pocket. If you don't do that, it'll do like the first layer of this one, first layer of this one, first layer of this one, and it'll go kind of by layer or by depth as it suggests here. And the issue with that's kind of how 3D printing works, and it's a lot slower because you need to cut out a layer of this pocket, then you need to go up, over, back down again. And that takes time to go up, over, and back down again. We want to save time. We want quicker cuts that take, so you're not there at the workshop till like 1 a.m. like I was all of last year. Or even like 2, 3, 4 a.m. That's how it goes. Sometimes even pulling all-nighters. God, what a great time. Anyway, so save time, do order by area. Okay, so that's all set. Now we can go ahead and hit OK. And you can see it kind of generates the toolpath of what the bit, again, is going to be doing. And one important note is if something's wrong, you're going to get either a red or a yellow little caution sign next to this like highlighted, selected adaptive 1 clearing pass. And there are a lot of reasons why that can happen. The first couple weeks when I started doing cam, they popped up all the time. I was Googling things left and right, trying to find solutions. And to be honest, Fusion's not great in the fact that they don't really tell you necessarily what exactly is wrong. They just say something is wrong, which is very, very frustrating. So I'm going to spend a little bit and tell you guys some of the most common things that I discovered while I was doing machining of why those errors came up. One of the most common ones is Fusion's actually smart, and so it knows how the diameter of the bit, and it knows all the dimensions of the part because we've given it all these dimensions. And so based on the settings that you've put in, it knows if the machine kind of can't do the certain thing you're looking to do, right? So one of the common examples of this is if you have a 0.25 inch bit and you're asking it to make a 0.26 inch hole, that's a very, very, very small cutting radius, which, like I said before, if you go in here, if your cutting radius is 0.025, it's not going to do it because you've got a 0.25 bit plus this 0.025 is going to make the minimum cutting radius of a hole 0.275, which is larger than the 0.26, right? So if you're trying to kind of create a hole that's like just barely bigger than the bit, and your minimum cutting radius is too high, it's not going to work. So that's kind of one of the common things you'll see. Another common thing you're going to see, what else is there? Oh, lead-ins and lead-outs. So say this say you have like a channel, like there's like a rectangular channel, right? That's 0.28 inches wide, which is only 0.03 inches larger than the bit. If your lead-in or lead-out is like larger than the 0.03 inches, it can't do it because it has to essentially go down and then lead into the pocket. But if there's material when it's trying to go down, it's not going to work. So that's why I tend to just completely turn off lead in and lead outs, is because you can get errors doing that. You can get a lot of errors during your selections. That's kind of where I find the majority of my errors. So if you do like tool outside the boundary, it doesn't know what it's going to be cutting out because it's not like there's no pocket outside of the boundary. It's just material, right? So that's an issue you can find. Sometimes if you're trying to leave stock to leave, if it's, where is that setting? Stock to leave. If the stock to leave is kind of, so if you have like a circle, right? Like let's say, for example, a 1 inch diameter circle, and you're trying to cut it with a 1/2 inch bit. If you're trying to leave like 0.8 inches of stock to leave, the bit's too big. It won't be able to, it'll create a hole that's too big. So you'll get an error from that. Other things you might see, I think that's the majority of the main ones that come to mind for now. A lot of the things have to do with kind of bit size. So bits not fitting in certain locations because they're too big, or the cutting radius is too large, things like that. So here we go. Here's our two tool paths so far. Okay, so now we're going to go over the final tool cut of this part, which is the third one, like the kind of the third of the 3 major tool paths you're going to be using, and that is this 2D contour right here. If we pull up our files, I think I might have one on this. Maybe not, actually. No, I don't. Oh, yeah. Let me go over smoothing passes first. Okay, so delete this. You can just hit cancel. Smoothing passes are important. I told you about the kind of the smoothing feature of the 3D adaptive clearing, but if you really want the most accurate possible hole, there's a better way to do it, and that is, again, using this same feature. And you can kind of see the settings are a little bit different. I've run it slower. Yeah, so I run it a slower feed rate, same RPM. The important thing to note is it's a climb cut, the full depth of cut, which means you have to use it after you've done the main pocket, and then the smoothing feature with a very, very small tolerance. So to do that, like I said, we're going to do 15,000 RPM. We're going to make this 20, 20, 20. And what's important to note, again, is the feed per tooth is significantly lower than when we do like the huge 3D adaptive clearing, right? And so that's kind of the main reason why I do a separate toolpath instead of just the smoothing feature of the like the before the pocket 3D adaptive clearing feature, is because we can now control this feed per tooth, which means a smaller feed per tooth, as you can see, means a much smoother cut, less vibration generally, less aggressive, smaller chips, which is more controllable, all those kind of good things, which, yes, they take longer, but for like a bearing hole, I always do this second toolpath with the 2D contour. So we're going to go ahead, we can choose the ones we want to make smooth pass on. Go ahead, again, choose model bottom with the neg 0.01. Neg 0.01, model top. Why is it not like that? Oh, 0.1 inch. There we go. Turn on smoothing, make this even finer, so 0.0001. And we want to again make sure we're choosing the climb again, more accurate, more precise. I'm going to turn off the lead ins and leads out, and hit OK. And you'll see that'll generate one tool path that'll follow along the edge of this curve, and it makes it really, really accurate. So the final tool path I'm talking about is, again, to kind of cut out the border of the part. We're going to be using a similar, or I guess the same 2D contour tool path. However, we're going to be doing things a little bit differently because we're going to have a lot more material that we're going to be cutting out. And so I think I might have it on here. Let me see if I do. Maybe I don't. No, I don't. All right, so feeds and speeds, again, 15,000 RPM. Aluminum generally is 15,000 RPM for a single flute. We're going to be cutting 35 inches per minute for all these. Again, you'll get faster doing all this stuff. We're going to be selecting this outside border. And the selection for the 2D contour isn't as complicated as like turning off the rest of machining like I did before. The stock contours, it's already turned off, as you can see. There's no like select inside. It's a lot more simple, which is good. So select the border border of the part you're gonna be cutting out. There's some preference on this, honestly, for turning on or off tabs. You can see what tabs are right on the right-hand picture. They kind of leave tabs, which will kind of keep the part connected to the overall stock material. This is really, really important when, I would say, when you have a lot of parts close together. I generally try to keep like the tabs on it. However, as you can see, there are now tabs on the perimeter of our part. And so with these tabs, right, after you machine all the parts, after you take the stock off of the CNC bed, you then have to go back and cut all these tabs. They leave like actually really sharp pieces of metal along the perimeter of the part left, which you have to then file down. So it's definitely a lot more work to have the tabs there. However, it's safer to machine. And aside from being safer, it's just a little bit easier. You can kind of leave the machine for longer periods of time by itself, not have to worry about these parts like coming off the bed as you're machining them and things like that. So it's up to you if you want to use them. I would say if you're not constantly looking at the machine, like if you're not sitting next to the machine waiting for it to finish as the tool path goes on, put on tabs. I chose the wrong selection. Make sure it's the bottom here. So for tabs, you can select the width is kind of the width of the bit, which is usually pretty good. I keep it at the width of the bit, which is 0.2, or diameter of the bit, which is 0.25. Tab height for aluminum, I generally do 0.04. It's a little bit less because aluminum's harder to cut. I don't want like really thick tabs that are gonna leave scars or marks on the final part. So 0.04. By distance is fine. If you want to do at point, you can like select which points you want to do, but by distance is fine for this. And you can select kind of how many tabs you want based on how far apart they are. So 5 tabs is a little bit too much. So if I go like 2.5 inches, we then get 4 tabs, which is pretty good for me. Next thing we want to do, again, select our height. Same thing as before. Model top, model bottom, neg 0.01, neg 0.01. We're going to do, so because we're not doing like a smoothing pass like we were for the last tool cut, we're going to do the same conventional, more traditional cutting style, which is right hand conventional cutting. And the thing to note here is when you're trying to cut out the perimeter of a final part, you want to make sure you turn on multiple depths, because if you don't, you're going to be cutting the entire thickness of the stock that you have, which could be like 1/8 inch, 1/4 inch, whatever it is, and that's a lot of stress on the bit. So make sure you do multiple depths. And I usually do for like kind of the outside border of a part, I usually do 0.025. And the reason for that is when you're doing like a 3D adaptive clearing, generally, or I guess, yeah, for the most part, you're only cutting kind of on like one half or one side of the bit because it's in a circular pattern. However, when you're doing a 2D perimeter, you're cutting on the kind of inside edge of the part as well as the other end of the bit, which will be cutting kind of stock material. So you're cutting, I would say, like 180 degrees, or like half the circumference of the bit, versus 3D adaptive clearing, which is only like a quarter. So it's a lot more stress on the bit, and that's why we have somewhat more conservative settings, such as a smaller depth of cut of 0.025. So change that, make it 0.025. No stock to leave. All this is all set. I turn off lead ins and leads out like I always do, and that's pretty much it. It's a relatively simple cut. You'll see now. We have, oh yeah, so we have, like, you can hit the little button down here to orbit around. We have the tabs built in. All the blue lines are the tool paths. Going to go around layer by layer. It's going to get to the bottom and kind of jump up and not cut out that material, and that looks pretty good to me. Okay, so now that I have what I think is the 4 tool paths that we're going to be needing to cut out the part. We have the drill hole, the huge pocket clearing, 3D adaptive clearing, the smoothing paths for all those pockets, as well as the final outer cut. What I always do, at least for beginners I recommend, is going into what is the simulation tab up here, and kind of showing the simulation of what the part is going to look like on the machine, which is actually a really, really, really helpful feature. So, to kind of get a better idea of what we're looking at, I make the tool transparent. I show tool paths that are only the tail, and then I turn on the stock material. And I also make it, where is it? Comparison. And so now we can see we can run this tool path. You can change the speed of how fast it goes here. So like a slower bit versus like a faster demonstration. And this is just going to show you, it's going to go through all the tool paths that we've created. It's going to show you what the part's going to look like after it's all done. And it's going to show you a lot of really important things, right? So it's going to go ahead and clear out all this material, yada, yada, yada. Going to go around the outside of the border, leave those tabs. And we can see a couple of really important things here just from the simulation. So for one, in CAD, we had the radius of these corners kind of going deeper in, and because our cutting radius, I believe it's because our cutting radius is so much larger, we're not going to be able to get into all the way into that corner. And so a couple things you can do. We can turn down our cutting radius, which will help a little bit. But really, you've got to be aware of this when you're doing CAD, right? You've got to make sure that the fillets that we're putting in here is accurate to the bit size we're going to be using, or like that we want to be using. You also see the tabs here. If we have stock all the way around, we're going to have also tabs over here and here. If not, we're only going to have tabs in these two places. But I want to go back and show you, kind of see if we can get rid of as much material that's left over here as we can. So that would be the adaptive clearing, I believe. Let me see. Minimum cutting radius, we can make this 0. Hit OK. It'll regenerate the toolpath for us. Just like that. And we can go ahead and hit simulation again. Run it all the way through. And you can see, right? Even when we have 0 cutting radius, the fillet that we put on this corner is it's just too small. Like the bit can't get into that small radius, which is fine. Doesn't, I mean, it's only like a non-essential fillet right here. It doesn't matter that much, but just be aware of it when you're designing these parts for the first time. So that looks pretty good. We're going to be left over with this part right here. That's in green. We got the drill hole looking pretty good. The drill hole doesn't look like it's going all the way through though. Let me double check that. See? Right there, that's why. So I made it positive hundredths of an inch. We need it to be negative hundredths of an inch. And that's why you always run simulations, so you can catch little things like this. Let's go ahead and run this again. Put it through real quick. And that's much better. Now we can see we have the drill hole going all the way through. Everything looks pretty good. You can go ahead and hit close. And we're all set. So to get these, so these are all tool paths. You can see all the blue lines have a tool path. And we need to now transfer what we have on the computer here onto a flash drive, so that we can then plug that flash drive into the computer of the CNC router and go from there. So to do that, we're going to make sure that we're hitting the full setup button here. If you only select like drill, you're only going to be moving this up and down drill tool path onto the flash drive. Or if you only select like 2 of them, you can hit this and then shift and select 2 of them. You only be doing these 2, which can be helpful, right? If you have like multiple tools in this and you only want to be doing like certain tool paths or whatever it might be, you can just select one of them. But for now, because we're just doing the whole part in one go, hit setup and then hit post process. You want to make sure that, I believe it's open. Okay, so yeah, so we're using Linux CNC. There are a bunch of options. You want to make sure that you've selected Linux CNC, because that'll make sure that the NC file extension is .ngc. Because Linux CNC only takes ngc files and a couple of other weird ones. So we got ngc file. This all looks pretty good. We're going to hit post, and we're going to save it under test part 1 full cutout. And I kind of name it based on what it is. So say we were only, why can't, whatever. So say we're only doing the drill hole feature of this part, I'd name it like test part 1 drill hole, or test part 1 pocket cutout, or something along those lines, so we know exactly what this ngc file, this G-code file, is going to be cutting out. So we can put it under personal flash drive. I have a bunch of other projects I'm working on right now. And go ahead and hit save. And this is what the G-code is. You can see it's just a really long list of commands. 20,000 lines, I think I just saw, that are going to be going to the machine. And so this all looks pretty good. You can see these are the I's, the I and J right here. This is kind of the arc commands. If you don't have, you look to it, there are no I and J's. That means that the smoothing commands that we put in for like the 3D adaptive clearing and other stuff isn't going to be in there, and your hole is going to be off. But we have all that, which looks good. We have tool 1 should be at the top. T1, good, diameter 0.25. Z min is the thickness of the material minus the hundredths of an inch. Flat end mill. drill 1. This all looks really good. So we're going to go ahead and just hit X. And now we have the G code that we need onto our flash drive. We can go ahead and pull that flash drive out and bring it down to the router. Okay, so there are also a few other things that I feel like should be mentioned. Just to kind of summarize and wrap up this video. First thing that we didn't really talk about is how to insert multiple parts into one Fusion file. That way you can CNC machine multiple parts all at once. So to do that, first thing you need to do is open any file. So let's just choose my file right here. I can go ahead if I want to and rotate this around really quickly like this. And then to insert a second part into this, you go over it, make sure that you've kind of uploaded the files that you want to be inserting into this SolidWorks, or sorry, this Fusion file. You can go ahead, once it's uploaded, you can go ahead, right click and hit insert into current drawing. And it'll then insert it into the drawing and it'll automatically pop up. A important thing to note is the first part that you insert is going to probably pop up as a body, but future ones are going to pop up as a component. And that's important because when you go to hit move, if you're like selected the bodies tab, you can't actually choose this component. You have to go over, hit component, and then click on it, and you can then from there rotate it around. Another feature also of move is, as you can see now, the bodies are at different elevations. To fix that, what I usually do is hit this point-to-point thing here, select the bottom point of one and the bottom point of the other, and then move it from there. So that's how you get multiple things into one drawing. Another important thing I didn't show you guys is one feature. The other feature that you might sometimes use is a surfacing cut, which is this one. It's really simple. Pretty much you just select any surface that you want to machine. So if it's like that surface, for example, you can kind of click on that. It already has all the settings built in for the most part. And it'll go along and machine the top of this part. If for any reason your stock is greater than 1/8 of an inch, you can then machine the surface of it down to the desired thickness. But we don't need that. And then the last thing I want to show you is in simulations. Where is it? Simulations. You can actually go into statistics, and it tells you how long the machine cut is going to be. And so this machine cut is going to be 7 minutes and 7 seconds.